Hello everyone, and welcome to the Introduction to Support Vector Machines lecture. In this lecture, we'll discuss the formal definition of support vector machines, and then try to get an understanding of the intuition behind support vector machines, or SVMs. If you want the mathematics behind this algorithm, go ahead and read Chapter 9 of an Introduction to Statistical Learning. Support vector machines, or SVMs as they're also known, are supervised learning models with associated learning algorithms that analyze data and recognize patterns. They're used for classification and regression analysis. In this lecture, we'll be talking about their use for classification. Given a set of training examples, each marked for belonging to one of two categories, so binary classification, an SVM training algorithm builds a model that assigns new examples, or these test data points, into one category or the other, making it a non-probabilistic binary linear classifier. An SVM model is a representation of the examples as points in space, mapped so that the examples of the separate categories are divided by a clear gap that is as wide as possible. And that's going to begin to set the intuition for an SVM that we'll see later on through some plots and diagrams. New examples are then mapped into that same space and predicted to belong to a category based on which side of that gap they fall on. Alright, let's go ahead and try to understand the basic intuition through looking at some diagrams and some plotted out data. Imagine we have the training data below. Here we have two classes. We have a blue class and a pink class. And what we're going to try to do is a binary classification for new points. We want to put a new point on this plot where the horizontal axis is some feature 1 and the y vertical axis is a feature 2. When we put a new point, we want to determine does it belong to the blue class or the pink class. Intuitively, what we could do is draw a separating hyperplane. In the case of 2 dimensions, this is just a line between the classes. However, we have lots of options of hyperplanes that separate these two classes perfectly. Notice that the pink, black, and green line would all separate the blue and pink training points perfectly. The question then arises, how do we actually choose the line that separates these classes the best? What we would like to do is choose a hyperplane that maximizes the margin between the classes. So you'll see a diagram typically that looks like this, where you have a separating hyperplane, here denoted as the dotted line, and then a margin that extends out from that hyperplane. The vector points that the margin line touch are known as support vectors, and that's where the name support vector machines come from. Here we can see the encircled points that are the support vectors. Those are the training points that actually touch those margin lines. We can expand this idea to non-linearly separable data through the use of a kernel trick. That means if you take a look at the left-hand plot in 2 dimensions here, you may have a X label and Y label, and you'll notice that this data is not linearly separable because it's a blue circle in the middle of blue triangles and a red outer circle of red circles. And there's no way we can draw a straight line to separate these classes. However, through the kernel trick, what we do is we end up viewing this in a higher dimension. In this case, we look at a third Z label over on the right. Now we can see that this is separable in this third dimension through another hyperplane. You can check out YouTube for really nice 3D visualization videos explaining this idea, and if you want the mathematics behind the kernel trick, again, go ahead and check out Chapter 9 of an Introduction to Statistical Learning. Now that we've learned the theory behind support vector machines, we can continue our understanding by building these models with Python. We'll start with an example by predicting whether or not a tumor is malignant or benign by using a built-in breast cancer dataset that comes with scikit-learn. Then your portfolio project will apply these same concepts to the famous iris flower dataset. And then we'll learn how to tune our models with a grid search. Alright, there's a lot of really exciting concepts coming up, and I'll see you at the next lecture.